Welcome, and thanks for joining us for another exciting episode of Mastery Algebra 1. I'm Mr. Fuller, and this is a lesson from Chapter 1, Section 3, Types of Numbers. There are several important sets of numbers that you need to know. All of the numbers that we're going to be talking about fall under the category of what we call real numbers. And the first set that you need to know is called the natural numbers. These numbers represent the number of ways that things occur naturally in the world. 1, 2, 3, and so on. Now, sometimes people call those the counting numbers, but the official mathematical term is the natural numbers. Some of you might be wondering, well, why isn't 0 in the natural numbers? Well, it's unnatural for something to occur 0 times. It's unnatural for there to be 0 fish in the sea, or for you to have 0 eyelashes on your eyelid, as examples. So when we include 0 along with the natural numbers, that has another name. It's called the whole numbers. Now, I didn't make this stuff up. I don't think I would have made a whole new name for a number set that just has one more number in it, but that's the way it is, so you and I both have to get used to that. The next number set you need to know are the integers. Now, the whole numbers have all of the naturals in them, and the integers have all of the whole numbers in them. The integers are all of the whole numbers and 0, and the negatives of all of those values. The rational numbers include all of the other three, all of the integers, which include the whole numbers, which include the natural numbers. And the official definition is any number that can be written as a ratio or a fraction, a over b, where a and b are integers and b is not 0. Examples of rational numbers would be anything that looks like a fraction, anything that looks like a over b. For example, 2/3. That looks like a fraction, so that's a natural number. Even 7 is really a rational number because you can write that as 7 over 1, and then you can see the fraction form of that. 0 for the same reason. 0 becomes 0 over 1. Those are the same. So if you can write it as a fraction, a over b, then it's a rational number. Now, what about something like 0.333 with a bar over it? That's what we call a repeating decimal. That is also a rational number because that is the number 1/3. If you took 1 and divided it by 3 on your calculator, you would get 0.33333 going all the way across the calculator. That's an example of a repeating decimal. What if you had a decimal that does not have a repeat bar on the top? 5.667. That's what we call a terminating decimal. If there's no numbers after that 7, then we call that a terminating decimal, and that also is a rational number because you can write that 7 number there is in the thousandths place, and then the 6 next to it is in the hundredths place, and the 6 before that is the tenths place, and the 5 is the ones place. So we can call that 5667 over 1000, or 5,667 1,000th. So if you can write that as a fraction, then that's a rational number. Next, and finally, I suppose, are the irrational numbers. The irrational numbers are any numbers that you cannot write as a ratio or a fraction, a over b. So what are some examples of those? Well, any decimal that is not repeating, any non-repeating decimal, any non-terminating decimal, many square roots, like square root of 2, and some special numbers in math like pi and a number called e. Now I'm going to turn on my calculator here and show you what you get if you ask your calculator what is the square root of 2. You can see that your calculator shows you the square root of 2 is this long decimal, 1.414213562. Different calculators will show different numbers there because they have different amounts of room on the calculator to show you values, but eventually the calculator runs out of space. So it looks like it stops or terminates at the end with the 2, but technically it's a non-terminating decimal and there's no repeated pattern. You cannot write it with a bar. Same thing with the number pi. Your calculator shows you 3.141592654 and so on, and if it had more room it would show you a lot more numbers and they would not repeat and not follow, it's not terminating and it's not repeating. Same thing with this number e. You can see that e, according to this calculator, is 2.718281828, but it continues and it's not repeating the 1828. That's a little bit hard to tell just by looking here. You might have to just take my word for that. So those are all examples of what we call irrational numbers. So these 5 different sets are all different types of real numbers. All of these fall under the category of real numbers. At the bottom of your page 13A, you can see a diagram that represents those definitions in picture form. So the big circle going around the outside shows you that all of these sets belong to the real numbers. Later in the course, we'll talk about numbers that are not real. We call them imaginary numbers. But for right now, you don't need to know that. We'll teach you that when we get there. So the real numbers are really split up into 2 different groups. There's the rational numbers and then the irrational numbers. And within the rational numbers, there's all these other number sets. Notice the picture helps you see that the natural numbers fit inside the whole numbers, which fit inside the integers, which fit inside the rational numbers. So all natural numbers are whole numbers, all whole numbers are integers, all integers are rational numbers, all rational numbers are real numbers. Also notice that the number 1 over 0 doesn't fit with any of those definitions up above. That's what we call an undefined expression, and we're going to talk more about that in another lesson, why it's undefined. A lot of people are confused about what you actually get when you do 1 divided by 0, but that's not part of today's lesson, so I'll save that for another day. What we want to do next is we want to practice putting those numbers or matching those numbers with their appropriate categories. So at the bottom of the screen you can see a list of numbers that I've written in red. And what I'd like you to do in a moment is to pause the video and look at each of these numbers individually and decide which of these categories does it fit the best in. Is it a natural number? Is it a whole number? Is it an integer? Is it a rational number? Is it an irrational number? Now technically they're all real numbers, so figure out which one of the other 5 categories they fit into. I'm going to help you get started. I'm going to take the first number on the list here, the 6, and I can see that that's a counting number. If I'm counting 1, 2, 3, 4, 5, I'm going to land on 6 next, so I'm going to put that in the natural number set. 0, though, is not natural, so I'm not going to put that in the natural number circle. I'm going to put that inside the whole number circle. It's a whole number, it's just not a natural number. -3, because of the negative, can't be a whole number, so that has to fit in the integer set. So I'm going to put that next to the word integer. The next number, 1/2, that's an example of a rational number, or a fraction, 1 over 2. I hope you're writing these down on your notes page as I go. The square root of 3, well, you might have to ask your calculator, but 3 is not a perfect square. You can't do the square root of 3 without a calculator. So that's going to be an example of an irrational number. Now the rest of these I want you to do on your own and then check your answers in a minute. So pause the video and then figure out where each one of those belongs the best. And then when you're done, start the video again and see how you did. I've placed the rest of the numbers in the most appropriate set. So study these for a minute and make sure you've got them in the right place. I hope you didn't get fooled by 4 over 2, for example. 4 over 2 really is the number 2. It looks like a fraction, and you might have been tempted to put it in the rational number set. And it is a rational number. But 4 divided by 2 makes 2, and that's a natural number, so it belongs the best in the natural number set. Same thing with the square root of 25. 25 is a perfect square. You can do the square root of 25. It just gives you 5. That's a natural number, so that belongs in the natural number set. Next, what we want to do is use the information that we learned on the previous page to answer the questions on page 13B. You might find it helpful to look back at page 13A at that diagram to help you decide on these. But what we have to do first is we have to name all of the sets of numbers to which each of these numbers belongs. So if I start with the number -1, I have to decide which number set does that go best with. So that exercise that we did a moment ago should be very helpful for you on this. You can see that it's got a negative, so it can't be a natural number or a whole number. That means it's going to be an integer. So if it's an integer, the integers all fit inside the rational number circle, so it's also a rational number, and all of the rational numbers fit inside the real number circle, so it's also a real number. So if I'm naming all of the number sets, then I have to include integer, rational, and real. 1/3, 1 doesn't divide by 3, so that is an example of a rational number, and of course all rational numbers are real numbers. So number 2 should be rational, real. Now, pause the video for a moment and answer questions 3 and 4. Remember to list all of the number sets to which each belongs. Number 3 is a natural number, which means it's a whole number, an integer, a rational number, and a real number. 0 is a whole number, which means it's an integer and a rational number and a real number. All right, next what we're going to do is decide which of these number sets is the most reasonable for the situation that's being described. The choices we have are whole numbers, integers, or rational numbers. So if we're talking about shoe sizes in general, not just specifically your shoe size, but shoe sizes in general, should we be using whole numbers? Should we be using integers? Or should we be using rational numbers, and why? Well, since shoe sizes can be both a whole number like 5 or a part of a whole like 9.5, then we're going to need to use the rational numbers to represent shoe sizes because we can have half sizes. What about the number of siblings you have? Well, aside from the fact that we say we have a half brother or a half sister, really the best number set to use for the number of siblings is whole. What about in number 7? Which number set is best for the number of quarts of paint you need to buy in order to paint a room? Notice question 8 before you answer question 7. The number of quarts of paint you need to use when you paint a room. At first they sound the same, but they're not. When you go to buy paint to paint a room, can you buy parts of a quart? Well, you might be able to buy a pint, but I think that which is part of a quart, but I think the best answer there is you buy whole quarts. You buy 1 quart, or you buy 2 quarts, or you buy 3 quarts. You don't buy 3.17925 quarts or parts like that. You don't buy 3/5 of a quart. So I think the best answer for that question is the whole numbers. But for question 8, when you go to use the paint, you don't necessarily use the whole quart or all of both quarts. So I think in that case, it would be better to say rational number. We can use parts of quarts. Finally, let's wrap up with these last 3 questions, 9, 10, and 11. What we have to do, or what you have to do, is to decide if each statement is true or false. And if it's false, you have to give what's called a counterexample. That means an example that shows how it's not true. So let's get started with number 9. Are all integers rational numbers? Is that a true statement or a false one? All integers are rational numbers. That's a true statement. Any integer can be written with a 1 in the denominator, making it a rational number. 5 can be written as 5/1. -3 can be written as -3/1. So any integer is a rational number. All negative numbers are integers. Is that true? It's tempting to say yes, but that's because when we think of numbers, we tend to think only of whole numbers. What if you think of the number -0.5? -0.5 is not an integer, but it is negative. It's not an integer, it's a rational number. So this is an example of a negative number that's not an integer. That proves that all negative numbers are not integers. And what about number 11? Is every multiple of 3 odd? Doesn't take very long to figure out that that's false. 2 times 3 is 6, and that's an even number, not an odd number. So this is 6 is a counterexample. 6 is a multiple of 3 that is not odd. Thank you for listening to this lesson. Remember, do your best, forget the rest. Bye for now.